Bryan, wanna know a wafer?
No? Dallin? I hear think you know a lot about equipotential lines.
Well, I hear you think you know a lot about electric fields.
I guess the only way to settle this then is with the physics off.
Well, you're on, Bryan. Here you go, Bryan.
Alright, now hand me a Sharpie. A Sharpie.
You have a blue card or phone number?
I don't.
$3.23 right there. This is swell. $5.
Thank you. There you go, Bryan.
Alright, Dallin. Let's walk you through the basics first. Electric field is both magnitude and direction, because it's a vector. And every bit of it starts with this thing right here. It's called test charge. Test charge is +1 coulomb, and because in physics opposites attract, it's attracted to the negative charge and repulsive to the positive charge. See, if this positive charge were any more repulsive, it'd be you, Dallin. Now, it's important for you to remember that electric field is the same in a charge, which means that the electric field here is the same as on the inside of the charge. How do you measure the magnitude of the electric field? Well, I'm glad you asked. We have to start off with the force equation. Force is given to us by K, our constant, times Q1, Q2, all over R squared, which means the further our charge is from this charge, the less the force it has. Electric field, on the other hand, which is measured in newtons per coulomb, is just the force over the charge.
Alright, Bryan, I don't need your ad hominem tactics because, unlike you, I actually know physics. You see here, you said that the field is the force divided by the charge. Well, I'm going to say something totally crazy. The force is equal to the field times the charge. Okay? Now, watch this. Work is the dot product of force and distance. So the amount of energy that a particle gains is the force times the distance, and these are both vectors, so this can be negative. If it's positive, it's going to be gaining energy. If it's negative, it's going to be losing energy. Now when you have a particle in an electric field, such as this one, the amount of energy it takes to move it a distance d is the electric field times that charge, dot product with the distance. And the potential is the difference in one point, say point A, and point B over here. The difference between the amount of work done from B to get to A is the potential.
Alright, Dallin, that was okay for an amateur on schmecko-pashmental schmines. But I bet you can't guess what happens when we have more than one charge at the same time. Look at this. See, this is what happens when you have a positive charge and a negative charge for the field. It might be a little confusing for a slow-headed person like you, so let's explain this in terms of gravity. See, you can think of this a lot in terms of gravity because it's attracted to each other. In fact, gravity is a very attractive force, which, makes you the opposite of gravity. So basically what happens here is that our positive test charge is going to go away from the positive and towards the negative, so we can draw our field the same way.
That was pretty good, Bryan, but check this out. We have a particle here, right? It's positive. Here's the field. Now we're going to have a negative, actually let's have a positive particle here. If we want to move it in this direction, as we said, it's going to take work. So you're going to be increasing the potential. Now to move it from a point B to point A, the potential is going to be the potential at A minus the potential at B. Now we're only talking about the difference in potential. Now if you want to talk about just the relative potential at one point, we define the potential at a distance of infinity away, like the distance that people want to be from you, to be the point where the potential is equal to 0. Also, since the electric field isn't constant, it depends on R. When we sum the work done from one point to the other, to another point, the amount of work to move it to those distances is going to be different each time. So what we're going to have to do is force dot product with a very small distance, dx, and we're going to sum those as an integral from a to b, and that is equal to the potential.
Sure, maybe your schmalculus or whatever can explain equipotential lines and electric fields and all that, but I bet you can't guess what happens when alright, I got you cornered with this one. This! Haha, yeah! 2 like charges. And they're both negative, like your physics test grades. And they're repulsive to each other, like you're repulsive, and they're not attractive either, like you're not attractive. So basically what we see here is that because they're the same, they're repulsed by each other, so all the electric field lines are going away from the other charge. Got you with this one, Dallin.
You know, Brian, those electric fields you've been drawing have been pretty cute, but I'm going to take it one step further, okay? I'm going to draw the equipotential lines. These are lines where the potential is equal at each point on the line. They're going to look like this. These dotted lines. The thing about these dotted lines, the potential at any point on this is going to be the same as any other point on this equipotential line. And they're always going to be perpendicular to the field. Because when you're moving perpendicular to the field, there's no work done. So if there's no work done, it's going to be equal in the amount of work that had to be done to move from any point along here. So that's why they're going to be the same potential, and it's always perpendicular to the field.
Oh yeah, Dallin? Well, I bet your equipotential lines can't explain the Boltzmann-Planck constant of permittivity and... Hold on, give me a sec. It's my mom. Mom? No, not right now. I'm gonna physics off with Dallin. No, I'm gonna win. Fine, I'll take out the trash. I'll deal with you next time, Dallin.
Well, see you, Ryan. Wait, you have the money?
No. Do you?